Apologize. So the big issue here is I started my computer doing something and then I closed it and then it like froze on me when I got to class. So I couldn't just like turn it on. Okay, but I'm almost there. All right, almost there. So as soon as I get logged in and connected here, we're going to talk about analog signals today. I had a lot of fun preparing for this lecture, actually. Let me see if I have. Okay, I think we're good to go now. All right, so anyways, welcome to class today. Today we're going to talk about analog representations. And this is if you recall, we've been talking about 3D mathematics and how all that works. We can have to understand matrices, vectors, essentially sets of numbers, and what do you do if you need to multiply them together, add them together. The normal rules of arithmetic don't apply, and that's what we've been learning. So if it's helpful to think of a computer image in the same way. It is just a giant collection of numbers. And in particular, if you think about red, green, and blue, each pixel is like a vector in and of itself. So you have a screen full of vectors. So you basically have this three-dimensional array of numbers that we want to do things with, okay? But most of the time when we're thinking computer graphics, we're thinking, how can we recreate something that we see in real life? We want to kind of think of something that exists in nature, and we want to be able to visualize it, manipulate it inside of a computer. However, everybody here in this room understands that computers don't operate in an analog world, they exist. They operate on the principle of 0 and 1. 0 is not 1 and 1 is not 0. They operate on that very discrete level, and everything about digital computers works on that principle. So somehow along the way, we need to take things that we think of as continuous, say like a sine wave, and turn it into something that's discrete that we can then represent with a digital, to create a digital signal. So today, we're going to kind of talk about that. We're going to go over a little bit about analog signals and to get a sense for what happens when we put it in the computer, and kind of end up and look at images and how images are kind of represented. So one way to think of an analog signal is it's some kind of function with infinite resolution and it's continuous. So sine wave, for example, you can take the sine wave it's defined for any point x, not just the values that we might say a float or a double has in C++. It's every single, even the values that those representations cannot represent. There is a number for that. There's a real number representing that function. So we think of that as analog. So the discrete world, though, we have limited values. Even what we consider to be smooth and continuous variables, even those have limited step. They have to step in so many units. So let's limit our discussion to some kind of signal f of x that goes between -1 and +1. All right. A sine wave makes perfect sense there, but also because we don't need to, there's some niceties about staying within that range. Namely, if you multiply any number less than 1 by itself, it's always going to be less than 1. So it's bound. Whereas if you have a number like 2 times 2 is 4, and you quickly come up with numbers that you cannot represent anymore. All right, so we're going to limit our discussion to signals that have the values -1 and 1. So when we want to convert it to a digital signal, we have to have some way of converting it into some bits. All right, and we think of bits as maybe 4 bits, 8 bits, 16 bits, 32 bits, 64 bits. We like to use power of 2 numbers. And so one of the things I did was I took a little math program and used the truncate function, which basically just chops the end off of any kind of real valued variable. And I defined 2 functions. One is called sample, and the other one is called ADC, or analog to digital converter. And to some degree, everybody's used to this happening in the world. In fact, me talking through this microphone, I'm talking to the microphone, it's converting it into a digital signal, and it has to have some kind of sample rate. So maybe you've heard of like CD audio, 44.1 kilohertz, or DVD audio, 48 kilohertz, 48,000 samples per second, or 44,100 samples per second, different kinds of things like that. How many times do you measure, in other words? And then the analog to the analog to digital just kind of says how many bits do I want to represent that signal with. So minimally speaking, high quality audio would start at 44.1 kilohertz and be sampled at, say, 24 bits. That gives you plenty of range to record a jet engine and record the softest whisper that you can possibly do. There's a lot of range in there. All right. So we have these 2 functions, and just taking a look at these functions, the sample function will take basically take your variable x and just cause it so that if we have, we could have measure it 1 time, 2 times, 3 times, 4 times, however many times we want to measure in between that interval, and then just make sure that we only measure at those points. So if I put in a smooth, continuous variable x, it'll just give me those sample points. It'll make sure the function only evaluates there. And we'll see a visual depiction soon. And then ADC does a different job. What it does is it takes a signal from -1 to +1, and we multiply by the maximum value we would expect for that digital component to have. So for example, if it was 8 bits, it would represent the values 0 through 255. And if we were representing negative and positive numbers with an integer, it might go from, say, minus 128 to positive 127. All right. So this ADC will just make sure that it stays at those values. And so then I can take our signal, f of x, and we can approximate it by using the analog digital converter function and the sample function to measure it. All right, so let's see what that looks like. So here we have a sine wave that I've plotted, and you'll notice that our x's, our measure 0, 1, 2, 3, 4. Because it's a sine wave, we would expect this to cycle at 2 pi. So every 2 pi, we'd expect the sine wave to restart. Now, if we were to control the sample rate and only measure when x increments by 1 every single time, then it doesn't matter how much precision that we have as far as bits goes. You'll notice that we have a very rough looking version of our sine wave. In fact, we would think this is probably a very crude approximation of a sine wave in that it looks very asymmetrical. We would not expect this to behave the same. And that's simply because we're just not measuring the sine function enough times. So let's see what would happen if we just kind of increase the sample rate to 2. And so if we increase the sample rate to 2, you can see that we have a lot better resolution in terms of representing the sine wave, although we would say that doesn't exactly look like a sine wave. It looks like some kind of stair-stepped sine wave. In fact, if you were slowly listening, let's just say that your audio was, you're listening to a piece of music and this was modulating the volume, you would hear definite steps as it's going up and down. You would definitely notice that some digital signal was controlling the volume. So if you only had, say, 2 bits of resolution or 3 bits of resolution here, or in terms of you would definitely notice stepping. So we need something more. So as we continue doubling the sample rate, so this is 4, we can definitely probably use this. In some cases, it depends if we really need the precision or not. Okay, but as we continue sampling this, you'll notice that we get closer and closer. So here's us sampling it 16 times as x increments every unit, 32 times, already it's pretty smooth, 64 times, and lastly 128 times. I just went up to 128 because it looked smooth enough for me. So if we were just changing the sample rate, you can see that if the sample rate can cause your ability to detect signals of certain frequencies. So if you've ever wondered why, in fact, it's twice the frequency that you'd have to set in order to accurately measure that signal. So for example, humans can hear anywhere from say 20 hertz to 20,000 hertz. And it's very rare that you can actually hear anything at 20,000 hertz. But let's just say some people say they can hear that. So in order to sample it, this is called the, and I put it in the slides here, but it's the Nyquist rate. You basically double the sample rate. So if you were taking a look at like CD audio at 44.1 kilohertz, the maximum it can represent is a 22.5 kilohertz audio signal that you'd actually hear. So if you're going to sample anything and you know how fast it's changing up and down, then you have to take at least twice as many samples as the frequency range that you're looking for. All right. And then what you can do when you convert it back, and I didn't talk about digital to analog conversion, but I'll just briefly mention what that is. You have to be able to take, say, this digital signal and convert it back into an audio signal. So if you're doing that, chances are these square edges are probably going to oscillate a little bit because analog electronics tend to do that. When they get abrupt changes, they bounce a little bit. So what I would expect is you would hear this audio signal, say this sine wave, but you'd also hear the part when the analog electronics are responding to these abrupt changes. So you might actually hear frequencies higher than this one because you're inserting things that analog electronics are not meant to do. So what they do to keep that from happening is they'll add filters. So let's say if I'm converting this audio thing and this audio signal I know I need to filter some of that high noise that comes out of it. All right. And so the only way to really improve the quality here is just to sample enough so that when you send it, convert it back to an analog signal, you don't have any of those changes. The change is so smooth, you don't even notice it. Okay, so that's sample rate. The next thing we would want to look at is the bit depth. So how much precision are we storing in the Y direction? So over here, I have a bit depth of 2. In other words, we can store numbers from -2 to +1, all right? And so all I did was just remap these back to the original range of -1 to 1, so we can see that when you're converting something from analog to digital, sometimes you have problems with the peak values, all right? So in this particular example, we have the sample rate is set for full resolution, or in this case, I set it to 128 because we can't really tell the difference. But you'll notice that this one, we just don't have enough numbers to represent the signal, and as a result, we still get the stair-stepped problem. All right, so incrementing up to a bit depth of 3, you can tell that we're getting better at representing those higher outer range values. But it isn't until, let's see, this is depth 4, so 4 bits is 16 numbers that you can represent. So you can count that up. So if we're at the top, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and then 8 would be the bottom one. So we definitely have the full range here, though we can't, this is still not quite enough to represent the sine wave. So, and you can also think of this in terms of color as well, and we'll see that as we move on, that there's a reason why we can use a depth value of, say, 6 bits or higher to represent color, because at this point we're starting to get, by using 6 bits of color, we're actually, or of resolution, we're actually able to, I think, represent the sine wave pretty well. Although it's still not perfect, you still got stair stepping, but it's easy to see that it's easier to, I guess, increase resolution just simply by just changing how much depth you have in of your values. So let's go up to 8. So 8 gives us 256 values. And so we can see here that if we were measuring error, we would expect to see some error at the peak values for anything less than 8 for this particular example. Although nowadays there is a sense of this might be good for representing the sine waves, but maybe it's not good for representing range. So especially that contrast. So for example, if you go outside, the sun is significantly brighter than any bulb we have inside this building here. Okay, so if you're using your camera, I would expect if you're taking a picture inside this room, if you were to go outside on a bright sunny day, that the sun would quickly saturate the sensor with all the reflected light. So, and vice versa, if you're to have your camera adjusted for the outside light on a bright sunny day, and you came in here, chances are you'd have a dark image that gets produced because it's undersensitive to light due to the fact that we were wanting to look at reflected sunlight at the time. All right, so this might be good for representing certain kinds of signals, but not all signals, but 8 is pretty good. So there's been a push lately in graphics to increase the depth to, say, 10 bits or 12 bits. And that definitely gets us a big boost. So if you've seen HDR being advertised on TVs, they're trying to get to that problem. There's 2 problems. One problem is we don't have enough bit depth to represent high range or high dynamic range for images. And then 2, we don't have enough resolution for representing color on a monitor. So that's getting better all the time, but this is one of those issues that plays into that. Okay, so if we increase the bit depth to 9 or 10, we can see that you really can't see it on the projector. I would not expect to see this on the projector, but if you were to look at this on a high resolution monitor, you notice that the quality does get better. You're able to better represent values. Okay, now let's take a look at a different kind of function though. So I went ahead and did a frequency modulation on a sine. I put a couple of different extra sine waves modulating the frequency. And so now we have something that's a little more complicated to look at. And I thought it would be interesting to see what is the error. So we have a sense, like if we're looking at a signal, but we don't know what the error is, like how off is this sine wave versus the real deal. So let's take a look at this function, and the graph on the right represents the error of the original signal. So all I did is take f of x and subtract it from our sampled ADC, so we can see exactly what error there is. What are we not measuring? Okay, and you can tell that this is pretty flat, although there are some areas where we definitely are struggling to get some of the resolution we would like, and this would only get better if you increase bit depth, right? So let's look at a bit depth of 8. So let's go back down. So we're step down to bit depth, and now we have 8. So if we go from 10 to 8, we notice not as much of a problem. So depending on your signal, if your error can handle it, then you can just reduce the bit depth because there's no reason to use all that extra detail. Okay, but now as we start going down to say 6, and I use 6 because 6 is very popular in terms of graphics, or you have 5-bit color, 6-bit color. A lot of, surprisingly, I found this out, a lot of laptop monitors don't actually, they don't have full 8-bit depth on the color, which kind of surprised me at first. And this might not be true for some of the newest high-tech displays, but a few years ago, if you bought a screen and it said, 16 million colors, it's not 100% true. What it would do is it would just use some processing to, change the colors that were displayed in there. It was actually 6 bits per component. And so it would just do some processing behind the scenes so you wouldn't notice that. Okay, so you can just kind of oscillate pixels up and down a little bit, and you can simulate a color in between by doing that. But 6 bits of depth, and so now we can see that our error is getting much bigger. So this might actually start to matter depending on the application that you want to do. Going down to 4, we would expect to see a lot of error with the signal, and in fact, that's true. So as we work our way down, then I didn't feel like it was necessary to go any more down on the bit depth because we know we're already dealing with a lot of error here. For a bit depth of 4 means you're representing your whole signal with 16 values. So yeah, we understand there's going to be some compromise there. Okay, so let's take a look at sample rate. So if we measure often, so in this case, we're measuring 128 times every time x increases by 1, then we can see that our signal still has pretty good error. And once we go to 64, then we notice that going back and forth, we have a change. So it's getting worse, but maybe visually you can't tell the difference. This is if we divide, so now we have, we're sampling 4 times less now at 32. And now you can tell there are some areas where we get significant errors in the measurement of this analog signal. And going down to 16, so this is 1/8 the sampling time. Now we're getting some significant errors. And of course, we can see the corresponding error in the wave that we're looking at. But it is helpful sometimes if you're really trying to deep dive and find out how off am I from my original signal, then you might want to do some kind of error comparison and see where that is. Okay, and then going down, you can tell that we can get some pretty significant errors. So this is, but sometimes you might need to approximate something and it's worth dealing with these, but this is a good way of finding out error. Okay, so now let's look at representing images. So any questions so far representing analog signals? Okay, so we looked at I'm going to call it a one-dimensional example, right? That might be like example of color or something. So images have the same thing. So instead of sampling, we might call resolution, right? So maybe you picked up a camera and your phone might have like say a 7 or 8 megapixel camera, but maybe you spend the money and you get some kind of camera with like 25 megapixels. Or you combine several cameras together. Sometimes you get gigapixel resolution. It just depends on what you're looking for. So resolution is the our version of saying sampling. How often are we measuring light? Like what interval do we get? And then secondly, bit depth. So how accurate are those measurements from pixel to pixel? Now, we will see here that the way that we represent the color, we normally think of as red, green, and blue. All right, but it's not the only way to represent color. For example, a lot of video is actually not represented as RGB, it's represented as YUV, where you have a luma component, that's the Y. And so just as a reference, Y just kind of means how bright it is. So in this, this formula down here, 0.2126R plus 0.7152G plus 0.0722B is the recommendation 709. That's what's used for encoding DVDs, I believe. And this is how you take a red, green, blue image and convert it to black and white. So I don't know if anybody's watched a black and white movie before, but you may have noticed, or wondered, well, what's the color of the hair? Because we see all different color of hair. We see brown hair, black hair, red hair, blonde hair. And you watch a black and white movie and you're wondering, what was the original color of the hair? That's kind of an interesting idea. And so this is essentially, though, the calculation that goes into figuring what that is. So you'll notice that predominantly green is the major component because our eyes are most sensitive to green. And then secondly, we're most sensitive to red, and then lastly, the blue range, all right? If we have time today, I want to show you a graph of the CMYK color chart. They've actually done experiments because your eyes have rods and cones. Everybody heard of rods and cones before? No? Anybody know how the eye works? No? A little bit. Okay. So actually, this is a good time to pause and take a look at that. So your eyes have rods and cones. The rods are your most sensitive, I guess, if you will, and they measure intensity of light. Okay, so ironically, if you were to look at, if you're up at night and there's no moon in the sky and you're outside, you're probably seeing very, very little color. It's all basically your rods responding to the available light. Now, if the moon is out, though, then you have some reflected light, and then you do sense color. All right, this is in the darkest environments, your rods are the most sensitive. Now, the cones are what's responsible for detecting color, and they have determined that cones are most sensitive to light in the red region, light in the green region, and light in the blue region. All right. Interestingly enough, and so how they do this is actually show people different spectrums of light, and then they ask them to say, what color do you think this is? And so then they measure from all the participants in the test, they measure how many people thought this certain wavelength was this color, how many people thought this wavelength was this color, and what you end up getting is 3 Gaussian-looking distributions centered around red, green, and blue. And what's kind of interesting is that the red, some people, you'll notice that there's a Gaussian wave around red, but there's also a little dip or area around blue as well, where some people just kind of think, well, I think I see blue, but it's actually a wavelength of red. So the red cones are kind of sensitive to blue light, or vice versa. Your blue ones are also sensitive a little bit to red. And I think that comes into play when we're looking at colors like rose or purple, those kinds of, because your eyes are not as sensitive to those, but yet we can see purple. Like if you look at the rainbow, you can clearly see purple, even if you couldn't, but on a computer you see purple, but you're actually seeing a mix of red light and blue light, but you think it's purple, okay? But in real life, though, if you look at the rainbow, you see the purple, the violet, which is actually not a color that your computer can produce. except your eyes think it's purple because of the sensitivity that intermix between red and blue. Okay, so I think that's interesting. So as an interesting side note, we're all kind of used to the idea of mixing red, green, and blue, and on a computer display. And so when we mix red, green, and blue, we get all the different kinds of colors. So when we do that, though, we always kind of think red, green, and blue is like that's just how you mix colors. But that's not been true the whole time. In fact, before the 20th century, most of the time painters would mix the colors red, yellow, and blue, and that's how they would get all the different kinds of colors. So we're going to talk about color models in a different lecture, but I just wanted to kind of mention that it's not always just been red, green, and blue. That's relatively new, I think, historically, that we think of colors that way. Anyways, going back to YUV, all right. So we're used to seeing RGB, but YUV, Y is the luma, that's the intensity, that's like the black and white image, and UNV is the difference around the blue and the difference around the red. So what we do is we basically separate the color completely out of the image, and we can reconstruct red, green, and blue based on the brightness and the measurement of how not blue or how blue is this signal, and how red or how not red is this signal. And we're going to see where that kind of comes into play. Okay, so just like we talked about, so I have an image here that I took in, I don't know, I think this was in New Mexico. And the way that when we look at the image, we see it as the image. But in reality, what's happening is that the projector is actually shining a red light, a green light, and a blue light next to each other. And sometimes they even use different patterns in this one. But because you're so far away, your eyes, the light kind of blends together by the time it gets to your eyes, so you don't actually see pixels unless you're like really up close and looking for them. But it's kind of, this is the representation on your image, so we actually have to have them laid out side by side for us to see them. Okay, so we mentioned resolution earlier, and so resolution is kind of our ability to sample a real image. So if we were to pretend that the image on the left is an analog version of what we see, then the computer image we take is really more like a set of pixels that are next to each other that really have no idea what the pixel to the left or the pixel to the right is really doing. Okay, so it's discrete. So this is how we represent images in a computer. They're all discrete. The goal, though, is that if we were to take this image and increase the number of times or number of pixels, then eventually we get to the point where we can't distinguish the pixels. Okay, so and most phones nowadays have a high resolution display on there, so that for the most part you can't tell where the pixels are. It looks like a smooth, continuous image. Okay, so the next thing that we can control is bit depth. All right, so what I've done over here is I've taken the image on the left. So generally the image on the left will be our reference image, and the image on the right will be our modified image. Okay, so I took the image on the left and I have reduced the levels. So all I did is I used it's called posterize, where you take the image and you say, I only want this many intensities of light. So it more or less maps to the same image. But in this case, we're saying instead of using 8 bits of resolution, let's use 7 bits. Okay, and how about we do this? You can raise your hand when you tell the difference. Okay, if you can tell the difference between the image, feel free to raise your hand. Okay, so here we go. This is 128 levels. Now we're at 64 levels. And so if you remember when I told you about 8-bit panels versus 6-bit panels, this is the same thing as saying a 6-bit panel. And for all I know, this projector might only be showing 6 bits of color.
I got a difference.
Oh, you found a difference? Okay, very subtle. It took a while though. Chances are, if this was a movie, you wouldn't even know, right? Okay, 32 levels. still a little bit more difficult. 16 levels. So it's becoming obvious. The sun, I think the darker areas is what gets hit the most. Okay, so at 16 levels, it should be pretty obvious. And I don't know, let me look at the projector. Not as obvious on a projector, but it's plain as day on my monitor over here. Okay, 16 levels, 8 levels. Yeah, okay. Everybody should definitely see 8 levels over here. So this is using, what, 3 bits of information? You can store this image with 3 bits of color information. This is 4 bits of color information. You wouldn't want to do this on a monitor, but depending on what you're displaying, you don't necessarily need all the accuracy. Okay, now here's the same 8 levels again, but this time I'm reducing the number of colors so that the image on the left is capable of showing 24 million colors, and the image on the right is only capable of showing 256. So one way of increasing the amount of pixels you can store as far as memory goes is simply just say, let's just choose 256 of the colors that most represent what this image looks like, and then let's go ahead and use those colors, all right? So graphics in the 90s and 80s definitely had very limited amounts of colors that you use to represent the image. Now, if I were to use a 16 color palette though, like let's just say we want to pick 16 colors to represent the image on the left, and that's all that we get. Well, then you can see significant banding on the right, but there is some techniques to kind of combat that. So one of the techniques is called dithering, where you use patterns of pixels of different colors to represent pixels of different colors. So this is that same image with 16 colors, and by using dithering, you can't tell the difference. I mean, you can on my monitor over here, but if you really needed to chop that down in size, as far as sampling goes, there are ways of doing it. This works the same for two-dimensional signals as well, like audio and so on. There are ways that you can add dither to the original signal, so you can have higher resolution with the digital, even though it's not, you may not have a lot of bits to work with. Okay. All right. So this is mapping colors with 16, and this is on the left side. We have the palette mapping with just 255 or 256 colors, and the image on the right uses 16 colors dithered. But if you notice, I didn't use dithering on the image on the left, and if you look carefully, you can see banding artifacts like over here, but you don't see them on the other side. So ironically, even if you had more colors, the dithering makes a significant improvement for image quality. Okay, and this is just to show you that when it comes to representing images, there are ways to approximate the original so you can't tell the difference, all right? And then this is using a web optimized palette. So there are some palettes out there that are, deliberate choices of we're going to have these colors represented, and that way it can display on devices that don't have a lot of color. Okay, so you can use dithering as a way of, and the image on the left is the full image. The image on the right is the paletted image. Okay, now, funny enough, you can actually take other computers, and they'll have like very simple palettes, and you can, ironically, you can use those to map what an image might look like on those systems as well. So this is a Commodore 64 palette, which is very popular. And normally when you think of Commodore 64, you think of games that look like images on the left, where they seem really bright, very colorful. But ironically, if you use dithering and use those colors, that doesn't mean you can't represent more sophisticated images, which shows that color has maybe not as much impact on the image as the resolution does, or even intensity.
Dithering is reducing the resolution of the model, right? Effective resolution.
Well, we're talking color, yes. Color resolution. Yes. Versus, now I'm going to show you this next image, though, this is not how it would look on a Commodore 64. So this is more what it would look like. If you took into account the other limitations, right? So if we just isolated color, that's not enough to say this is what it would look like. So what I did was I also reconstructed an image that had the appropriate horizontal resolution, because the pixels are double wide on a Commodore 64, and the resolution is 320 by 200. So what I did was compensated for that in this image. So yes, the colors are not the problem. The image resolution, so how often you're sampling, is a problem. Okay, and that's just to kind of show how interrelated the two concepts are kind of interwoven together. Any questions so far? All right, so that's a look about the color and resolution. Okay, now let's take a look at color representation, so how we choose to represent an image. All right, so we know about resolution, which is how many pixels wide, how many pixels vertically are we storing a sample, and then two, how much depth do we have for our colors? What can we represent with the colors in terms of red, green, and blue? Like if you have 3 bits of color or 8 bits per channel. But there are different ways of representing besides red, green, and blue. So here's what this image looks like. If we were to decompose the image into its red, green, and blue channels. Okay, so we'll see that we have high resolution for each one of these. And if you were obviously to take one of these channels out, it would obviously cause this particular RGB thing to suffer. Like you would all of a sudden, it's like, nope, no green, or there's no red. And in this particular image, I chose this because you have colors from all different, you see all the varieties of colors in there. Whereas an image like this, it is kind of concentrated in certain colors. Okay, so one of the first ones that we can choose to represent is to divide the color into the hue, which is red, orange, yellow, green, blue, indigo, violet, RGB, and then saturation, so how gray is the image, and then lightness or value. Okay, we're going to show the difference because there's two. One's called HSV and the other one's called HSL. All right. So in this image, you'll notice that the representation has a big change here. So for hue, you notice that we have huge splotches where the color is significantly different. All right, and the second image over here on the right. Let me see if this has. Okay, this represents the saturation. So white means that the color is really saturated, and black means there's very little saturation. So in other words, these doors over here in the background are pretty low in saturation, or the white, low saturation, because it's really more of grayscale. And then the image on the bottom here, we have the value. All right, so value here goes from, we think of black to white, and the other complementary version of this color representation is HSL, okay? So if we look at HSL, you'll notice that you can really tell the difference between V and L, because in one system, the value 0 is totally black, and the value 1 is completely white. Whereas, go back here, V represents whether, more of a, I think it's like a, how far do you get to full saturation versus how white it is, okay? So yeah, this is a common way if you want to pick colors, based on where they are in the rainbow, and how bright they are and how saturated they are, okay? But let's say you want to print this image out. So I think we discussed a little bit that printers don't print red, green, blue. We actually use a different kind of ink. We use cyan, magenta, and yellow. And what those let us do is, because we're printing on white paper, they are actually, light is reflecting on the paper, but we don't want it to, we want it to absorb or not reflect light. So we pick the complementary to those colors. So for example, cyan, which is blue and green, is going to reflect red light. So so when it goes in there, it's going to basically not allow red light to come through. Let's see if I'm right on that. I always forget. So this is called CMYK, and K is called the key color, and that's a way, because if you were to print on a LaserJet printer, chances are it doesn't have maximum representation of black values because of reflecting on the white paper. So they'll actually add a separate layer of black ink that you can then get those darker colors off the printer paper. Okay, so before we talk about K, let me just skip forward and look at the cyan, magenta, yellow. Okay, so if we just represent the color with the complements, then if we look at red, for instance, we see that in the cyan image that they're almost black. And that's because that's the opposite of red. Okay, so this is an interesting color combination where this is subtractive in nature. Okay, so when we see red, in the cyan image, the red is subtracted off the image. And when we look at the magenta image, we see that green is subtracted. All right, and if we look at yellow, the blue is subtracted. Okay, so it kind of feels weird when you look at CMY because this is a subtractive color model. Okay, so now when we add the key value, you'll notice that some of the images just get darker because you don't have to lay as much toner down for those particular, and that saves on color toner, so that's one of the reasons why it's used, but also allows you to better represent the images black and white. Okay, so lab color, I'm not going to talk too much about this, but this is, I'll talk about it in a little while. I just don't want to spend too much time on lab color today. Okay, but I do want to talk about this YCBCR. So does anybody remember using component video? You remember using component video, maybe at an Xbox One or something. And you had the three cables. You had like the yellow and the greenish one or a red one or blue one. So you plug all three of them in here, and it represents these three signals. So the luma, which is the black and white, and so if you look at the top left black and white image, that is the actual representation of the intensity, all right, absolute intensity. And then the other ones represent the color, all right. And what's interesting, and we're going to see exactly why these are very popular for video encoding, is because remember we were talking about how your rods are more sensitive than the cones are. They're way more sensitive. In fact, your ability to distinguish images really has more to do with your rods because they're dealing with contrast than your cones. Okay, so let's take a look at that. So over here, I'm using a one-to-one image. So they are basically the same image. Okay, now I'm going to decrease the bit depth, and you may have noticed that the brightness decreased, but we're basically only using I want to say we're using 1/4 the amount of colors. Okay, and when we look at I remember how I did this. So we're basically reducing the color range. All right, so if we look at these images, I just basically only allowed a certain number of bits to represent the color parts of the image, which is the CB and the CR. Okay, so you really, aside from maybe the slight drop in contrast, which you could have adjusted by compensating for the intensity, can anybody tell a difference between the color? Like, do you sense that you lost color? Maybe. Okay. Yeah, in fact, that's where you would lose it. This is going down 16, so now we're decreasing Go back for 4. Go to 32. 16. Does anybody see any significant change? I can see it on my monitor, but can anybody see it on the projector? So it sounds like perception-wise, it's very difficult to tell the difference. Okay. This is 64. Okay, you can probably tell with 32 very easily. So what that means essentially is that you can chop out quite a bit of color from your image because your eyes just aren't that sensitive to the changes in individual color, as opposed to the overall brightness of that color. Okay, and I did one as there's 16 levels, so this is 32 levels. I think I did this one to represent, okay, P represents posterized. So this is the original image, but now there's only 32 levels of each. And if you think about that, 30 or 16, let's take a look at the 16 levels. So 16 bits, right? If we had an original RGB image and we were using 8 bits per channel, that's 24 bits total. But if we maintain using 8 bits for intensity and we use 16 bits to represent the other two images, we basically have reduced the total requirements for our image into 2 planes, right? So 16-bit color. We can use 16-bit color to represent more or less the image that we're looking at the right, which is why YUV is very popular for video compression, because you can just chop the color quite a bit as long as you don't touch the intensity. Make sense? Okay, so lastly, let's talk about compression. So in the one road image with the tree, that is approximately 1707 by 1024. So in memory, if we were to, and this is very important to think of images as how much memory are they using. So that image in memory, if we were to load it up, uncompressed, is about 5 megabytes, okay? And there are different kinds of compression. So there's lossy compression and there's lossless compression. Lossless means we don't lose any detail. Lossy means we are willing to give up some detail in exchange for smaller sizes, okay? So PNG, it's very common lossless compression, and we can tell that it reduces it from 5 megabytes to 3.5. So that's a pretty sizable difference when you're concerned about not losing detail. So there's no reason not to use it, okay? And then we have JPEG, which is a lossy compression. It means it throws out details. And for the most part, it's very popular with photographs because you can throw out lots of details and nobody even notices the difference, okay? So you can tell that a 90% quality JPEG is now close, just a little bit more than 10% of the size. I mean, that's a pretty big reduction in quality. And the JPEG thinks it's about 90% of what the original image was, okay? Now, as you reduce that further and further down in size, say down to 10%, then you can get significant size savings for the same resolution image. But the question is, well, can you tell the difference though? Okay, so in this case, I have a JPEG image up, and technically I'm making a JPEG of a JPEG because I took this image with JPEG mode on my camera, but we'll just ignore that for now. Okay, but when we go down to 90%, can anybody tell the difference from the two images just looking at it? Not immediately. Let's take a look at 75%. I'll go back between. I couldn't really tell on my monitor here. 50%. 25%. Yeah, it probably is. But if we look back here, you know, we went down to 95 kilobytes towards the end. You can tell on my monitor not the 10% pretty clearly, but I would say that probably until you get down to this range, and you'd have to look in areas like the door on the right-hand side is where I really noticed it, that you can see definite banding happening. Okay, but it goes to show that you can compress a lot out of images, and it's really doing it in the color area. It really is reducing how much color is used to represent those images. So there is a type of, so I use another comparison here that if you were to compare, say, a 25% image with a 75% image, I have a little error chart here, which you have to look very carefully, but you notice that the main error happens around the tree, the border of the tree and the surrounding environment. But it's very, very little error. You probably would not be able to see that on the original image. Okay? All right. So texture compression. So this is a very popular thing to do, especially if you're trying to target devices. You want to pack as much texture maps into your graphics card as possible. So there are some ones called ASTC, and it's kind of derived from the S3TC compression that came out in the 90s. And it was kind of under patent protection for a while until a couple of years ago. But now there's like a standardized way of doing texture compression. And what they'll do is basically, you know, can you really tell the difference from having 8 bits per pixel to 2 bits per pixel? So they actually, what they'll do is they'll chop down little small sections so they use little 4-color palettes, and then they can reconstruct the image that way. And so I think it looks pretty good. You can cut down a lot of detail. Okay, so that's what I had prepared for graphics as far as the slides go. And then I was going to talk a little bit more about OpenGL. So, but are there any questions about anything we talked about today as far as color goes?
I thought JPEG compression also compressed the texture of the image somehow.
Yeah, I think there is some kind of an adaptive thing you can do where it'll examine small pieces and decide whether it should reduce those. So it does some kind of like perception and calculation on it. If you were to like reduce the amount of color detail in that area, or even like, which was kind of funny. I was at my friend's house and he had just gotten this brand new TV set, and I was joking. He was like, "Is it, you know, what do you think of the image?" And I said, the image is so good, you can see all the compression artifacts perfectly. So that's our long-running joke, I think, for the last 2 years. That's because I said that, you know, the TVs are so good now you can see all the compression artifacts. But you're right on that. They will examine different parts of the image and decide which one needs the most adjustment. Where can you lose the most visual detail without perceiving that you're losing it? Okay, so there's some perception calculations that kind of go into JPEG. And then there's even more options like, you know, how much, when it's creating the JPEG, you know, should it, they'll use these ratios like 4 to 4, 4 to 2, 4 to 0. In other words, horizontally and vertically, how much should it reduce color detail?
Do you know if anyone's doing adaptive compression based on human attention? So like you train a neural network to figure out what people eye track to most of the time, and then use that to adaptively compress different sections of the image?
I think there is some work going on there, but I'm not too knowledgeable about that area. But I know there is some work as far as like, because VR, you put VR goggles, if you can enhance the area that you're looking at, then that would definitely help out. Although I did see a presentation earlier this year at i3D 2019 where they pretty much focus on real-time graphics. So NVIDIA was showing off some new technology they have called adaptive shading. And so what they'll do is they'll actually examine the image as it's being generated and watch to see if they can increase the shading rate or decrease the shading rate in certain areas. So instead of, so obviously you need to shade along the edges of a polygon, but maybe on the inside of the polygon, you don't need to shade as much. So maybe you just use one shader to color 4 pixels instead of using it to color 1 pixel apiece. So they're actually showing how they can adaptively sample shading. So I think you could take that principle of like eye tracking and say, well, let's see what the perception difference is if you just use adaptive shading, turn it way down for areas you're not looking at and turn it way low for areas you are looking at, see if that makes a big difference. And that might be a big performance increase because yeah, virtual reality, you're rendering images faster because you have to hit 90 hertz as a minimum benchmark versus the 60 we're used to hearing about in order for it not to cause a lot of big problems. So, yeah. Yeah, go for it.
So different displays have different matrix patterns. What are the major impacts of those? Because like I've heard that more modern OLEDs, they're running into a lot of problems with how you perceive those because they're using a pentagonal dot pattern, whereas LCDs have classically used like a 3-block pattern. That would be a 3-block array.
Right. So yeah, that is one of those things where, I put the one image with the red, green, and blue because that's how it used to be. But there are different patterns. Let me back up to that slide. Okay, but there are different patterns that you can. I actually downloaded off this website, said how to make an image look like it was, put on a screen capture. And so I downloaded this pattern with the red, green, and blue, and just pasted it on top as a separate layer, and then multiplied the image on the bottom. So, but this is a full clip of what it looks like. And so, yeah, they are laid out nice and neat. I remember back looking at my monitor when I was, this is in the 90s, you could see them laid out. But when you look at LCD arrays now, they're not laid out this way. Some of them are laid out so they're staggered, so they're not even on top of each other. So the representation you're talking about, even then, you can get more detail out of a display by using a clever pattern rather than having exactly 3 red, green, and blue for each pixel. You can kind of simulate, you can remove some of the color signal and then still not perceive, or you can still have better perception. So yeah, there is some work on there. How much can you take away, create a bigger panel that isn't as expensive to manufacture? So that definitely is a element there. All right. So let me close that. Okay, so before I was coming to class here, I was working on the OpenGL, kind of how do you do OpenGL. I'm trying to find the full screen button here. All right, and the one thing, close these extra. I'm gonna move this out of the way so I can see what I'm doing. Here we go. Okay. The one I need to skip. Just make sure this runs. As soon as I have this graphics thing ready to go, then This is what happens when you don't compile before you come to class. You make changes and then they don't work. Oh, gotcha. Need to include the libraries.
Oh, Mike.
Mic drop. Oops. Okay, so I'm just gonna pull up the chair over here so that I can see what I'm doing. Use both hands. So if you ever wanted to know how to include libraries in Visual Studio without having to like manually add them, then you can use this pragma comment. And it gets ignored on Linux, so you can just do it anyways.
So is Pragma just a Visual Studio thing?
Yeah.
Ah.
Pragma it's officially part of the C specification. It allows the compiler to oh, okay, I know what I did. This particular, I'm trying to put my graphics engine back together again. Well, let's just let it compile. In the meantime, we'll just do stuff in the background. So one of the first things that we were doing was clearing the color on the screen. Oh, I decided to quit on us. I think so. Okay. Get out of full screen mode here real quick. Go into debug mode. Maybe this will work. Let me see if this will. Cross my fingers. I hope that this doesn't crash. Success. Okay, so I'm working at like building this thing back up again, but let me just show you some of the technologies that I have in there. So I maximize this. Move this out of the way. Okay, so I'm using this GUI called Dear IM GUI, and this is a C++ library that you can basically integrate graphical user interface stuff into your program. It's really good for testing, for like adding debug stuff to your code. So let me turn off some of this stuff here. Okay, and I can use this to kind of control all different kinds of parameters. This is really useful, you know, if you're trying to if you're trying to test different parts of your program and you need it to. All right, so this is a way of showing everything that's around. Go back to 17 here. Change the exposure down. So I can actually generate, you know, a physically based sky inside this program here. And we're loading up 3D models. And these are you know, different kinds of things that we might want to do. So as we're developing like sophisticated 3D engines, I actually spend a lot of time designing user interfaces, putting together, you know, so you can try your shaders out, you know. So I wanted to spend time writing GLSL shaders, but I also was spending a lot of time changing code and recompiling and then see what it does, and then changing code and then compiling and seeing what it does, changing code, recompiling and seeing what it does. And it's actually a huge time sink, just going back and forth in that repetition. So what I wanted to teach you all is, you know, how do you go about, if you're making your own 3D engine, how do you go about incorporating some of these best practices into your program? Now, if you're using Unity or Unreal, a lot of this or something similar is already built into it. So what I would encourage you to do is figure out, you know, if you're going to be working on, say, BRDFs, reflectance functions, and so on, or even models, you know, go ahead and add some amount of control to your demo so that you can actually manipulate things and see how they work, okay? So in this particular case, I have an ability to, like, say, change exposure and gamma like I would expect to see in a bigger engine. I can set up some shader values that I pass into the shader so that I can control. So this particular shader, and it's actually kind of funny because when shaders first came out, the whole point was to write a nice short shader because that's going to be executed like that many times per second. Now that you can buy video cards that have like 1 trillion floating point operations per second, you know, if we were to take a look at a 1K by 1K image, that's 1 million pixels, right? And that's 3 colors, so that's 3 million, you know, separate RGB, right? So we'll just go with 1 million pixels. And if you wanted to render that at 60 frames per second, you would need to be able to have some shader that could run 60 million times in 1 second. So you do the math, 1 trillion operations per second, 60 million required, you know, that's how much you got to divide that number by. You're still talking over 1,000, you know, theoretical steps that you could put in a program, and you still have 60 frames a second. It's actually pretty remarkable how much computation that you can do. It used, you know, because I would ask the question, I think I asked the question last time, or maybe we talked about it in this class, you know, how do you feel about doing like a square root for every pixel? and nowadays, when you're talking about normalizing a variable, you wouldn't kind of bat an eye at that. That's normal. We just do that. Okay. So, for instance, let me load up a shader so you can take a look. I'll load up this shader. I'll load up this. I call it the slow shader, but really it's running so fast you can't even tell the difference. There are other things in the program that take a lot longer to do than the shader that I'm running is having a problem with. So We go here. And I'll show you this particular shader. Go up. I don't remember the full screen button. There is F11. Okay. All right. So let's look at this particular shader. These are all like inputs, and you can use structures. It's a C-like language. If you're using Unity, then they're using the CG language, which is closer to the DirectX flavor. All right. And they're here. I might have to start paging down here. Some physically based sky code for reading a texture map. Let me just go all the way to the bottom. Yeah, this shader is over 2,000 lines of code. So you don't have to be scared about writing shaders anymore. You can really write like some sophisticated programming stuff, although there are some weird things you have to do to get around some of the idiosyncrasies of programs that run on a GPU because they're not general purpose 100% yet. They're close to that. But in this case, debug choice is 17. And so what I'm doing here is I'm iterating through a number of lights. And so I do a function prepare light, then I do a diffuse BRDF calculation, and then I add some specular in, and I add environment reflection, and more or less that's what it's doing. Okay, and so you can make some sophisticated shaders. So, I mean, in this class, there's going to be a limit to what you can do as far as learning how to, you're not just going to write a 2,000 line shader in this class. It's just not going to happen. But you can take some and implement some basic shading principles inside your own programs. But what I hope to show you, especially over the course of the next few weeks, is how can you build up an application with a GUI that you can then manipulate things that can dynamically load up shaders. So over here I have the scene graph, and so I can go in here to the different 3D models, and I can manipulate their matrices. So here, I can't move this graphic. Maybe I can turn to see the bunny. So if I wanted to, I can rotate. I can change, and you can see the matrix over here. So I can change the rotation matrix, and you can see exactly what I hope to do is build up a little GUI so we can play with the matrix transformations and see what they do. All right. And then 2, I wanted to build up a user interface so that we can take a camera and play with the quaternions and see how you would animate quaternions on a Bezier path. And I think that would be also pretty useful. So yeah, and then we can change the translation so I can move it up or down. And this is what happens when you change the W coordinate. It kind of messes with the projection space. Let's set that back to 1. Okay. And Z, all right. Any questions? That's the world transform. So this is the absolute position of the bunny. And the bunny, as you can tell from the rotation, that's what gets divided. So you really want to keep that 1, but this just kind of shows you that when you reduce, as you reduce the value of W down to 0. Actually, I don't know this might be controlling something else. Might be mistaken on that. It's just the way it's acting. Okay. Then I can load the identity, so I can move it around. No, that is changing the W. Yeah, because down here, this is a 4x4 matrix. And so you can see that the W, it normally should be 1, but we're scaling it, and that's going to affect the projection. Yeah.
That's scaling the whole thing towards world 0.
Right.
Okay.
I think that's effectively what it's doing. Otherwise, yeah. But that's part of the nuances of like, or one of the reasons, a good reason why you might want to like play with something like this to kind of get a feel for what is the matrix doing? You know, what is W, this homogeneous, how does it act if you put values other than 0 or 1? Okay. All right.
Scale down an object by multiplying its x, y, and z by the inverse of W and reduce the W.
Well, you don't want to play with W. What you would actually do is inside the your rotation matrix, the diagonal. So if you want to scale it by 2 in the x direction, you change row 1, column 1 to the scale value for the x direction. And then row 2, 2, or cell 2, 2, you change for the y direction, cell 3, 3 for the z direction. You leave W alone. You don't touch W. So in this case, I probably shouldn't have W in there at all, so you can't mess with it. But maybe I should change that to scaling. You know, we changed the scaling amount, and that would affect the diagonal of the first of that upper 3x3 matrix. Okay, and then going back to the shaders, if we were to take a look, because we're almost out of time, if we were to take a look at the vertex shader, which is what we run on all the vertices of the, those are the points that the geometry is defined by. We would see actually a very short program. Okay, so let me just go down. This is actually a lot longer than it needs to be, but basically what I do here, because I'm also doing things that you need for shadow mapping. But the basic thing is we need a normal matrix. So we have normals, which are they're perpendicular to all the surfaces. But what I do is I have the model view matrix. And remember we talked about, you have a projection matrix, a camera matrix, and then I have what's called the model view matrix. This is the world matrix. Okay. And then what we do is we just multiply this by the incoming vertex position, and that's how you transform your points. So the vertex shader can be very, very short. In fact, let me see if I have an even shorter version. This is for Z values. Yeah, this is just using the model view matrix and the projection matrix, and then we're just outputting a position. So this can just be very short. You just throw in a couple of constant values that you would change for the shader, and then that's just about it. And even this one should be pretty short as well. Yeah, this is about as long as a vertex shader needs to be. And normally you can just reuse vertex shaders left and right because they're all doing the same thing. We're going to see in the next couple of weeks how you definitely want your geometry pipeline, everything to be as consistent as possible, because everything has to work like a particular way or it doesn't work. Okay, I think the last thing I had for today, so let me just close this, was the homework assignment, which I still need to upload to GitHub. I still need to upload to the class website. I will do that before 8 o'clock tonight. I'll do that. Well, I'll do that right now. No reason to wait. Okay, I just need to get Word up. Okay. CS484. And I remember, I think I had mentioned that there was let me view width. Okay. That I had not decided yet on the additional requirement number 1, right? So the first one is do 1 hour game jam and answer the questions, rules for your video game. How does a player win or lose? How's the game started? So additional requirement 1, I decided, okay, if you want to research some classic video games in the Atari 2600 and come up with like 3 things of a mechanic you might want to utilize in your project, or for your game, that you do this weekend. Okay. So this should be pretty fun and not a whole lot of extra effort, because it's not really a programming assignment. And then requirement 2 lets you show how to do transformations in the 3D engine you chose, or to make a diagram. And then draw.io is what I use to make this particular diagram. So that is going to be the homework assignment for this one. So I remember we talked about it on Monday, and I said I hadn't come up with the additional requirement, that last one. So I'm going to say this is a PDF and upload it to the class website. Otherwise, we are finished for the day. Any questions? Okay. All right. I'll go ahead and we'll end the meeting.